अस्सलाम वालेकुम जी, आपको मेरी आवाज़ आ रही है? आप लोग मुझे सुन सकते हैं भाई? क्लास शुरू करें? कितने बजे शुरू करें? इट्स 8:14 राइट नाउ।
यस सर, आवाज़ आ रही है।
अच्छा अच्छा। तो लास्ट क्लास है तो आप लोग क्यों मोरल डाउन क्यों है आप लोगों का इतना ज़्यादा? शुरू करें क्लास कि वेट करें?
स्टूडेंट बहुत कम है, वेट कर लें।
शुरू कर लें। Okay ji, Bismillahirrahmanirrahim ji. Welcome to the last week in your course. Okay, so this is steel structure CE 409, and today we are going to discuss the topic that is we call plate girders. Okay, so today we will have some short introduction to the plate girders. Just what we call plate girders and what they look like and why we need plate girders. Okay, so today we are going to discuss the plate girders and we are going to review that how we can compute the flexure capacity of plate girders and how we can calculate the shear capacity for plate girders and how what are the different components of plate girder. Okay, so this is the content of today's lecture. First we will have an introduction to plate girders, like what we call plate girder, how do they look like, what are the different components of plate girder. Then we will go through the American Institute of Steel Construction requirements or recommendation about plate girders. There are some guidelines regarding the selection of plate girders. Like, plate girder is not a hot roll section. Okay, it is primarily a flexure member. Okay, but it is made of plates, and you made the plate girders by combining different plates. And in order to combine all the plates, you need some connection like welding, bolting. So there are some requirements which are set by American Institute of Steel Construction on the plate girders regarding its geometry. Okay, and then we will see that what is the recommendation of AISC about the flexure capacity of plate girders. Like, if we want to evaluate, you want to calculate, or you want to establish the flexure capacity of plate girders, what are the different limit states and what are the different formulations we have to consult with to come up with the flexure capacity of plate girders. And that would be followed by an example to demonstrate the procedure, that how plate girders are designed or evaluated for flexure capacity. Then we will go through the shear capacity of plate girders, like how to compute or how to establish the shear capacity in plate girders, and how to check the plate girders, are they adequate in resisting the shear. Then that with the procedure or the recommendation that is set forth by the American Institute of Steel Construction, they will be demonstrated with the help of this example. Okay, now I will grab my highlighter or I will grab my laser point. Okay, so we will have an introduction, we will have we will have a introduction to the flexure capacity evaluation of plate girders. We will have some discussion on shear capacity of plate girders, and this discussion will be demonstrated with examples. Okay, so the first thing is that what we call a plate girder, like किस चीज को हम plate girder कहते हैं. Okay, so a plate girder is a built up section. Okay, it is a built up and mostly it is a I section. I section means like this one. Okay, so this is a built up section, it is not a hot roll section first of all. Okay, so if I grab my pen, that plate girders and what is the difference between a wide flange and plate girder. So you should know that plate girder plate girder is not a hot roll section. Okay, hot roll section means that uh, you cannot find the plate girder in the manual. Okay, like we use AISC manual to find the or select the different shapes, like we select wide flange section, we select channel section, we select T section. So plate girder is none of these sections. You cannot, these are not called plate girders. These sections are called hot roll section, and you can find the detail and about their properties and their integrity in compression and integrity in flexure, like whether they are compact, they are non-compact, they are cylinder. So you have some recommendation and guideline in this manual. But plate girder is a different story. So they are not hot roll section. Okay, mostly they look like ice shape section. Okay, and these plate girders are used to carry heavy loads which cannot be economically carried by this I section or hot roll I section. Like the demand, like the demand, like for example, bridges is demand is very high. Okay, is very high. Okay, and you need a section which has a greater depth. Okay, like you need a 40 inches or 70 inches deep I section in order to resist the load which is coming on your structure or which is being transmitted from the slab to this beam. So what you are going to do, you cannot find a suitable section in the manual, then you have to go for this built up section. Built up section means that this web and this flange, they are have to be welded together or they should be riveted together. Okay, in order to construct this type of section. This type of section is like called plate girders, and this is connected, or the different components of the plate girder are brought together by the help of some connecting techniques. So we know that there are three different techniques. We have riveting, we have welding, we have bolting. So the plate girders are made by riveting, or mostly you can say nowadays by welding the steel plates. Okay, so plate girders are made out of steel plates. Okay, so there are three different components in the plate girders. Okay, the first is web, the second is flanges, and the thirds are the stiffness. So if you see in this figure, so this is a web. Okay, this is a plate which is called a web. These are called flanges, and in addition to these two components we will have a stiffeners. Okay, which are provided along the longitudinal direction of this plate girder. Okay, so these type of components are called stiffeners. Okay, and then we have two type of stiffeners. We call vertical stiffeners, we have these horizontal stiffeners. Okay, so in order to increase the buckling capacity of this web, so we have to provide this stiffener, so we have to brace the length of this plate girder. Okay, आप लोगों को समझ आ रही है?
Yes, sir.
Okay, thank you. So now you can see this is another version of the definition. Like they different people define this plate girder in different manners. Like you can see this is an example of plate girder. Okay, so the figure is showing an example. Okay, this is example of a plate girder. Okay, so when you look at this figure, so you will see that the dimension or the depth of this plate girder is very deep. So this you cannot find in your manual. Okay, so there is another version of plate girder, like what we call a girder or plate girder in steel structure, is that a plate girder is a flexure member. Please remember, this is a beam which is required to carry heavy loads on relatively long spans. Okay, so we know that when we increase the span or when the span is very large, then you have to use a section which is the depth of that section will be more, as compared to the section which is used on a small spans. Like in bridges, you need the spans are very large, okay, then you have to come up with some sections, okay, and that section, or mostly in bridges, the beams are called plate girders, because the loads coming on the bridges, like for example, this is a bridge, okay, so in this bridge, the load intensity or the load on the deck is very high. So this is representing demand, okay? This is your demand, okay? Now this demand has to be transferred to these pillars. For example, these are piers. So on the piers, you need to have some beams, okay? And when you see the demand and when you see the span, so what you think that the hard roll section will be not sufficient to cover this demand. So you have to go for this built up section, okay? So please remember that plate girders are built up sections, okay? Built up sections. If you remember from our previous class that when we were discussing the base plates, in the base plates we have seen that we have used a box, okay? अगर आपको लास्ट क्लास में थोड़ा बहुत याद हो तो वी वर डिस्कसिंग बेस प्लेट्स और हमने कहा था कि वी विल यूज अ बॉक्स, okay, and why we use that box, because the load that is coming on the column was very high, so we used a box which was consisting of 16-inch by 16-inch dimension hollow box, okay. So there are some situations like one other problem in Pakistan we have that we do not have hard roll sections, okay. Please remember, in Pakistan there are no almost hard roll sections. Hard roll sections are not available. If you go to the field, okay, so then you have to make, but the plates are available. So the plates you have to connect and you have to come up with this thing. So mostly you will be dealing with plate girder when you will be going into field. And for example, you got an opportunity to work in a consultant, then you have to deal with plate girders, okay. So a plate girder is a cross section, like there are different forms of plate girder, okay, and the most widely used plate girder shape is this I shape, okay, this shape, okay, and it has a, and other than this I shape we also have this box shape, okay. So these box shape has more torsional strength, okay, like you can see that this box, they are superior, okay, they are superior to this I shaped girders, okay, in terms of torsional capacity, okay. Torsional, I'm sorry for my spelling, okay. So if you have to choose an I, or you have to choose between these two, so I think you should go for this box shape, box I girder, okay, box plate girder, okay. This is box plate girder, okay, and this is I plate girder, okay. So the detail is that if you, before the welding was not used that extensively, so this was the shape of the plate girder when you join different plates have with the help of these rivets, okay. So when you use welding, so it looks very aesthetically, it looks very good as compared to the riveting, okay. And in riveting you use more steel as compared to the welding, okay. So the detail about the box girder and the I-shaped girder is provided here, okay. Like you can see the box section which has two webs. So in I shape you have just one web. In box shape you have these two webs, okay, and two flanges, okay. So this is a flange, this is called a flange, this is called a flange, okay. So the box girder is torsionally superior shape and can be used when the large unbraced lengths are necessary, okay. Like it's talking about that you are working heavily and you do not wish to use the stiffeners, so then you will go for this box shape, okay. In a moment we will see that uh, what are the different components like of plate girder. So the, you can see that in the plate girders, like this is the components, okay. Let me write it down here. These are the components of plate girder. Okay, the first component is the web, the second component is the flange. Okay, what is a web? The deep central vertical plate, like please see that the vertical plate is called web of plate girder. It separates two flange plates by a required distance. Okay, so the web is responsible to resist the shear that is developed in the plate girder. Okay, so the flange, what we call flange, or flanges are flange plates which are horizontal elements. Okay, like this is a plate built up I section. So this is a web. This is a web. Okay, and these are the flanges. Similar, they are have the same definition as the wide flange section. So horizontal elements which are provided at the top and bottom, like the flanges are provided at top and bottom, okay, and which is separated by a web. The main purpose of flange plate is to resist the bending moment acting on the girder, okay. So the top flange resists the bending moment by development. We know that when we have this type of beam, so there is a load on the top, we will have compression, on the bottom we will have the tension. So the bottom flange will be in the tension and the top flange will be in the uh, compression. If we are taking this example, this is a simply, if it is a simply supported girder, okay. So the next is the stiffness. So in this figure, you can see that this is a flange, very thin, tiny plate, okay. This is a web. But apart from that, you also have these vertical elements, okay. These are called stiffeners. Okay, now stiffeners can be classified into two categories. So you have vertical stiffeners and you have horizontal stiffeners. Okay, now vertical stiffeners are provided at right angle to the flange. Okay, like this should be a right angle. Okay, and they are also called as transverse stiffeners. They are again classified into two types, namely end stiffeners and intermediate stiffeners. Like in term, when we are talking about vertical stiffeners, they are subdivided into two categories, into, like you can say, the end stiffeners, and we have intermediate stiffeners. So the word, this is the classification. The end stiffeners are provided at the ends, okay, and intermediate stiffness are provided in between the start and end of the girder, okay. So one thing you should pay attention is that they make a panel, okay. This is a panel, this is a panel, this is a panel, this is a panel, okay. So what is the function of end stiffeners? End stiffeners are provided at both the ends of the girder. They receive the load from the beam and transfer it to the support. Okay, so these end stiffeners are, they also take the load and they help in transmitting the load from the girder to the support. And these stiffeners, vertical end stiffeners, are also called the bearing stiffeners. Okay, okay. So in plate girder, some part of end portion of the web is subjected to due to these loads, the web of the section may be crushed. Okay, okay, like web also receive like some compression. Okay, if the stiffeners are provided, so they can safeguard or they can enhance the capacity of the webs. Okay, so please remember that end stiffeners are also called the bearing stiffness. Okay, and this concept is very similar. Okay, like the stiffeners is, you can say, like stiffeners, you can say they are bracing of girder. Okay, and apart from vertical stiffeners, you also have horizontal stiffeners. Okay, so now this is something about the intermediate stiffness. Okay, intermediate stiffness are required when there are a concentrated load that is acting on plate girder. Okay, like this, like this, like this. intermediate stiffness, okay, in order to prevent it from buckling, or in order to increase the integrity of this section. So you also have to provide this vertical stiffness, okay. So when the thickness of the web is very less, then the web may buckle due to shear. In that scenario, you also have to provide the intermediate stiffness in order to increase or enhance the flexure, okay, in order to prevent, okay, okay, in order to prevent the web buckling, okay. I'm sorry, you need these stiffeners, okay, intermediate stiffeners. So the thing is that there is a web, there is a flange, there are a stiffeners, and stiffeners are vertical stiffeners and horizontal stiffeners. The vertical stiffeners are of two type. We have these end stiffeners, we have these intermediate, and stiffeners are also called the bearing stiffeners, okay. But if there is some concentrated load that is acting on plate girder, then you, in order to enhance the uh, flexure capacity of the web, you also provide these intermediate stiffness, okay. So horizontal stiffeners are provided parallel to the flange plates, okay, like this. They are also called the longitudinal stiffeners, okay. So you can go through this definition, okay. So there are all the detail is provided on this slide, okay. So the plate girders are fabricated separately, okay. Each may be designed individually to resist the applied action, and using proportion that ensures self-weight and high load resistance. Like it says that if there is a demand, so this web, sorry, these flanges and these webs, okay, they can be of different thicknesses, okay, like different thicknesses, or they can be made of different materials, okay. I'm talking about the web and flanges, okay. Now you can use a different material plate, okay, like you can use this A992, you can use that material. For this you can use A36, okay, depending on, you can use them, you have the choice, okay, because this is not a hard roll section, okay. And there is no like for example in compression you have a very high demand, flexure demand. In tension you have very less demand, so accordingly you can use different thicknesses for flanges as well, okay. So you have the liberty in the plate girder to go for this type of design, okay. So changes in cross section, like there is also considerable scope for variation of cross section in the longitudinal direction. You know, designer may choose to reduce the flange thickness, so we have already discussed that, okay. Like you can go for different flange thicknesses, okay, for your plate girder, okay. Equally in zone of high shear, designer must choose a thick web plate, okay. So webs resist the shear, okay. So you can use different, the web may be of different thickness, flanges may be of different thickness, so you have a choice in this plate girder, okay. So material, as I told you, that you can use different material for different components, okay. Like you can use different material for stiffeners, you can use different material for webs, you can use different material for flanges, okay. Okay, high grade steel might be employed for zone of high where you have high moments, high shear, so you can use different material, okay. So such type of girders in which you use different type of materials, you call them hybrid girders, okay. So plate girders are normally designed to support heavy loads over long space, however long spans, in a situation where it is necessary to produce an efficient design for by providing girders a high strength to weight ratio, okay, to produce lowest axial flange force for a given bending moment. The web depth must be made as large as possible, okay. The web in the, like in the plate girder, you should have the thickness or the depth of the web is more, okay, so in order to enhance its capacity, okay, but to reduce the self weight, the web thickness must be reduced to minimum, okay. So you, what you do in plate girders, the web have higher or greater depth, you can say depth, but thickness is less, okay. As a consequence, in many instances, the web plate is slender, okay. So when you increase the depth, but when you decrease the thickness, and that is the case, so this makes webs slender, okay. Okay, so this is, please note that this is important, like, okay. Okay, in plate girders, the web buckling does not determine the ultimate strength of the plate girder. Okay, this is, remember, plate elements do collapse when they buckle. They can possess a substantial post buckling reverse of resistance. For an efficient design, any calculation related to the ultimate limit state should be the, okay. So, like in plate girders, okay, there are two types of strengths, okay. The plate girders, you can say that plate girders derives strength, okay, by before buckling, like before buckling, it will have some integrity, and due to which it will have some strength, and after buckling, okay. So it derives the, like you will see that in case of shear, like there are two types, like but before bending of the flanges and after bending of the flanges, so it has strength, okay. It doesn't mean that if the flanges or the webs are bent, so it will have no strength, and this is a serious limit set, no. So before the buckling and even after the buckling, it provides or it has some strength left. You have to take that into the account, okay. So, so I will come back to you. Like how many of you are in the class? I have to check. Okay. Any questions so far?
No, sir, it's going too well.
I don't think so. That is going too well, but let me summarize it. Okay.
Yes,
Plate.
sir.
Yeah. Ahmad, you wanted to say something?
Yes, sir. Say so far so good. But if you
Like,
want to summarize it, it would be better.
okay, okay. Plate girder is, please remember, plate girder is a built up section. It is not a hot roll section. There are three components of plate girders: webs, flanges, stiffeners. Stiffeners are of two types, like the end stiffeners and the intermediate stiffeners. Okay. So, and the web of the plate girder is responsible for developing the shear strength. Okay, the shear force is resisted by the webs. Okay, flanges are responsible for the flexure capacity of the plate girders. Okay, so please remember that. Okay, so with this, I will go through the requirements of AISC. Okay. So as I told you that webs are cylinder in plate girders because you have a larger depth of webs. Okay. Let me grab my pen here. The depths are high, but the thickness are very less. So this makes the webs of plate girders very cylinder. Okay. Let me, okay. Webs of plate girders are cylinder. What does it mean, cylinder? It means that where is that? Okay, I have to add a new slide here. Yes, like you remember from your beam design that we have been using a curve. Okay, which type of curve? Like you remember that. So if my pen is not working, let me see. Yes, now it has started working. Like we have used this type of figure. Remember, on the x-axis we have some moment. Okay, on y-axis we have some depth to thickness ratio. Okay, like this, and we have this type of curve. We said that okay, this is compact, this is like inelastic buckling, and this is elastic buckling. Okay, so let me write it down that this is compact section, this is non-compact section. Okay, so this is cylinder. So what the discussion or the abstract of the discussion so far is that plate girders are cylinder. Okay, okay, but we have to check that. Is my plate girder cylinder? Is it compact? Is it non-compact? And if you see this figure, so on y-axis you have this bending moment, and on x-axis you have this depth to thickness ratio, and this depth to thickness ratio is of web. Okay, so if I go back and I go to the AISC requirements for selecting the geometry of plate girders, so there are some guidelines, and these guidelines are based on this web depth to thickness ratio. And there are certain limits, okay? Like if the depth to the thickness ratio is less than this value, and no, sorry, is it if it is greater than this value and it is less than this value, then your web will be a cylinder. Okay, it will be classified as cylinder. Okay, okay, like let's go through the text. Okay, whether a girder web is a compact, non-compact, or cylinder, it depends upon this ratio. Okay, what is h? This is h. Okay, this is given here, h. What is thickness? This is thickness here. The width to the thickness ratio of web, where h is the depth of the web from the inside face of the flange and to the inside face of the flange, and tw is the web thickness. Okay, excuse me. If you go to the manual, so in the manual this section says that for doubly symmetric, this shape, this is a doubly symmetric section. Okay, and if I make this section, the flanges are of different widths, and this is not a doubly symmetric section. Okay, for this the requirements are different. Excuse me, can we take a break for 2-3 minutes?
Yes, sir.
Okay, just give me times, I will grab some water for myself. Okay, so just give me a moment. Okay, I'm back. I'm sorry. I don't know why I get caught by this cuff. I don't know. I have to see. Okay, we were discussing that how to check the slenderness of a web. Okay, like there are two limits here. You can see you have to have the depth to the thickness ratio, and if this depth to thickness ratio is falling in between these empirical values, so you can say that this value is you can say this is mp lambda p, and this is lambda r, I guess. Okay, if the web to thickness ratio is less than, okay, if it is less than this value, then your web will be compact. Okay, if the web value or the depth to thickness ratio falls in between these two values, so your web will be okay, your web will be a non-compact section. Okay, and if the value is greater than this 3.5.7 value you see here, so the web will be slender. Okay, so this, whenever you will be solving or dealing with this plate girder examples, whether you are evaluating like flexure capacity of the plate girder, first you have to check the slenderness of or the capacity of your webs. Okay, is it compact, non-compact, is it cylinder? Okay, okay, there is an additional requirement, and this requirement is for doubly symmetrical eye-shaped section. If you want to see the singly symmetric or the sections which are not doubly symmetric, so then you have to use different set of the equations, and you can find the set of equations, like set of equations mean lambda p and lambda r. Okay, and that is very different for the singly symmetric eye-shaped sections. So you can see that. Okay, so this is the, you can find that in sigY book, but I have not included in this slide, so that you might you may use in order to avoid the confusion, I have not included that information on this slide. Okay, now there is an additional requirement, and this additional requirement is that saying that to prevent vertical buckling of the compression flange into the web. Okay, now there is a limiting value. Okay, this h by v value. Okay, h by this depth to thickness ratio, like there is an additional requirement. Okay, and this additional requirement is for value, you can see a by h. So we know that h is the this one. Okay, this is h, but what is, we know what is a? So a is the distance between the stiffeners. Like for example, if I make a section, this section, this is a I-shaped girder. So in the longitudinal direction, I told you that we have to provide some stiffness. Okay, now A represents the distances between the stiffness. Okay, vertical stiffness. So you also have to check, you also have to satisfy this requirement, that this is the maximum requirement. Okay, it should be equal to this one if this is the case. Okay, if the case is this one, then the maximum value should be this one. Okay, when you satisfy this requirement or this requirement, so the compression flange, okay, there will be no vertical buckling of the compression flange into the web. Okay, so for all girders without web, okay, forget about, but for you, for the sake of your information, I have this slide. Okay, if you want to avoid it, go ahead and okay, but if you want to have a complete information, so just read it out, that this is an additional requirement on this web. Okay, so there are different recommendations, like how to check the compactness or the non-compactness or slenderness, and what should be the maximum ratio of depth to thickness. Okay, so there is another, that all girders without web stiffness. Okay, web stiffness to no more be greater than this one. Okay, forget about this one. Okay, but it is there when you are designing. So we are clear, like we have to check the webs web first. We have to check the web compatibility, or the is it compact, or is it non-compact, or is it cylinder. And we know that how to check it. Okay, on the previous slide, so we have seen some equations. Okay, basically we have to calculate this, and we have to compare it with the LP and LR. And LP is, if you go back, uh, for the students which are like me, which cannot absorb this information that from that slide, so I'm going to write it here. Okay, this is Fy, and this is, I think, this one, this limit. Okay, there is another equation which is lambda r, and this is about 5.70, and this is E by Fy. So this is representing this limit. Okay, so this is about webs. Okay, webs are plate girders. Okay, okay. Now, if you want, there are three limit states. Okay, let me write it down. Okay, there are three limit states. Three limit states for plate girders. In order to evaluate the flexure capacity. Okay, what are those three limit states? Okay, the first one is the tension flange yielding. Okay, tension flange yielding. Okay, this is the first limit state. What is the second limit state? Okay, for this limit state, you will have a definite equation how to calculate the nominal capacity of the plate girder. Okay, for the second limit state, which is the compression flange strength. So for that, you have a different equation. Okay, and for third is LTB, which are you are familiar with. What is LTB? So this is regarding the stiffeners. Okay, stiffeners, vertical stiffeners. Okay, this is related with the stiffeners. You have to compare the LB. You have to calculate LB, and you have to compare it with LP and LR. So how you are going to calculate the flexure capacity of a plate girder? So you can see that moment or the flexure capacity is due to the flanges. Okay, now you can see how, no, you have to calculate the bending moment which is developed in the plate girder for these three cases, and then you have to select the least one. One will be the capacity, flexure capacity of your plate girder. Is it clear?
Yes, sir. So far, so good.
I hope you are not joking.
No, seriously, sir. Right. It's very clear.
Okay, now first limit state is the tension flange yielding, and how we are going to evaluate this flexure limit state. For this, you can evaluate the first limit state by using this simple formulation. Okay, you have to use these values to evaluate the flexure capacity in the flange yielding limit state. Okay, what is FB? FP is it says that the flexure stress, so in the case, is the ratio between the bending moment and section modulus. Okay, when we are talking about in the elastic range, so we will be using elastic section modulus, and when we go to the plastic capacity, then this S will be replaced by this Z. Okay, now you see that there is no Z here. It means that you are in the elastic range. Okay, like how up to the yield you can use this, And if you want to use the capacity of the flanges which after the yielding, and you can go to the ultimate limit state, then you have to use this one, but the code does not permit it, okay? Because what I understand so far is the thicknesses of the flanges and the webs are very less, so you cannot develop this compact section, okay, or the capacity we are having in the beam section or capacity we were having in the hot roll section. We were going up to Z. But in this case, you can evaluate the flexure or nominal flexure capacity, which is based on tension flange yielding. So you can use this equation. Fy is the yield stress. Sxt is the elastic modulus of plate girder on the tension side. Okay, like you will have compression and you will have tension. Okay, over here you will have compression and over here you will have tension. This is the tension side, this is the compression side, okay? So you have to calculate the section modulus of the plate girder on the tension side, and you have to multiply it with the Fy, and Fy is very simple, for A36, for A992, okay? So you know that. So you are very good at evaluating the tension flange yielding. So if somebody says you can close your eyes, you said this is very simple, I can do it. The next is the compression. Then compression flange strength, how you are going to evaluate it. For that, you have to use this equation. Now, okay, in the compression side, you have to use this formulation. And if you see the formulation, so there are different variables. The first is SXC, elastic section modulus on the compression side. The RPG is the bending moment or bending strength reduction factor. And how you can calculate it? You can calculate it using this equation, okay? But in order to solve this equation, you need this AW, okay? And there is an upper limit which is set on this equation. This is, since it is an empirical equation, and this limit is set by this guy, okay, this guy. So you have to calculate these three values, and the most difficult part I think in this is to calculate this FCR, critical compressive flange stress, okay? And it can be yielding, it can be we have to check it local buckling, okay? Like if the local buckling occurs before yielding, so the FCR value will be less than this one. Let's see. Okay, now in order to evaluate the nominal flexure capacity, you have to see that the critical compression flex depends. You need this one, as I told you, that this we need in order to get the value, critical stress value. So whether we have to check the flange, which is a compression, which is on the flange, is compact or is it non-compact, or cylinder, okay? So you have to go through these, you have to check this, okay, in order to decide what will be the value of FCR, okay? If FCR, if I remember that if your section is compact, so FCR will be equal to this one, okay? But if it is not compact, then this value will be less than Fy. And how to find this value? There is a procedure here, okay? So you can see that first we have to calculate the width to thickness ratio of the flange. Then there are some equations in the AISC, okay? This is lambda P, this is lambda R. The same thing, okay? For example, this one. This is actually representing lambda P. Somewhere here you have this lambda R. So how to calculate this value, so you can use these equations. Okay, so in this equation, so you will see that in lambda r there is another term which is used kc. Okay, so this is a different value. So now, so in order to compute that value, you have to use different empirical equation, and the upper and lower limits are given here. Okay, so if your lambda value, this value, is less than this one, if you have you calculated lambda and this lambda is what is it is saying, let me see, if this lambda is equal or less than lambda p, so you will be in this zone. Okay, and in this case your flange will be compact, and in this case your FCR will be equal to Fy. Okay, if your lambda is between this limit and this limit, then you have to calculate FCR with a different formulation, and this is, I think, lambda, this is lambda p, lambda r, this is lambda p. Okay, so this is the thing, that this is a problem. Okay, in order to evaluate this limit state, you need this one, and in order to calculate this FCR, you have to see that your flange is compact, non-compact. Okay, if it is a cylinder, then you have to use different formulation in order to calculate this FCR. Okay, is it clear?
Yes, sir.
Okay, so the third limit state is the LTB. Okay, now this LTB is related with, you can call it the bracing length. Okay, bracing, you can call bracing of the plate girder. Okay, okay, now how to calculate or how to evaluate the LTB flexure strength? So you have to use this equation, same equation. Okay, now this equation and this equations is almost similar. Okay, but the, in order to check that whether the the length between the stiffness, like let me draw it here, like for example, so if this is a plate girder, why this pen is not working, so you might have this stiffness here. Okay, so this is, you have to calculate this length. If it is less than, so there will be no, if A is equal or it is less than LP, so there will be no LTB. Okay, if it is greater, then you might have buckling problem. Okay, so in order to see the capacity, so you can use this equation. Okay, so we know that this is the strength reduction factor, and we have to calculate this FCR again, and this Sx is the elastic section modulus on the compression side. Okay, so whether the lateral torsion buckling will occur depend upon the amount of lateral support, and this lateral support is the stiffness. Okay, if the end brace length is small enough, so yielding or flange local buckling will occur. Okay, before LTB buckling. So it is saying that whether lateral LTB buckling will occur depends on the amount of lateral support, that is that unbraced length. If the unbraced length is small enough, yielding or flange local buckling will occur before LTB. So there will be no LTB. In order to evaluate LTB, we use these different parameters. Okay, these equations in order to check it. Okay, but this equation uses this RT. So RT is the radius of gyration about the weak axis for a portion of cross section. Okay, so because we know that if this is a wide flange section, so along this axis r will be different, radius of gyration will be different, and along this axis the radius of gyration will be different. So you have to use the r value which is the minimum, okay? Radius of gyration about the weak axis, and weaker axis is those axis in which you have this moment of inertia, okay? Whichever axis is giving you this the minimum moment of inertia, that will be the weaker axis, okay? So you can read out this statement, okay? So but the thing is that if lb is less than lp, this lb is the unbraced length, okay? Let me write it down. lb is the unbraced length, okay? If it is less than lp, what is lp? This is lp. So there will be no ltb. If lb is between lp and lr, failure will occur by inelastic ltb, okay? And in this case, if you will calculate this fcr by this equation, okay, you need cb as well, okay? So you remember what is cb? आप लोगों को याद है? Do you remember what is cb? Any student who knows what is cb?
I guess it is the correction factor,
Yes,
but
yes. If the bending moment is like there is a curvature, then you have to adjust this one. You have to use. And CB value will increase or decrease the flexure capacity. What do you think?
yeah, if what?
If the CB value is greater than 1, it will increase the flexure capacity or it will decrease the flexure capacity?
It will decrease.
It will increase. You
Will
have to
increase.
check your beam notes, okay? If
Okay,
because
we have to multiply. Is that why? Okay, it will
yes,
increase.
you have to multiply. If it is 2.2, so it is increasing the flexure capacity. If it is 1, it will stay the same. And if you have this type of curvature in your bending moment, you have to plot your bending moment, okay, diagram, and then you have to see what value is the cb, and cb value, there are some empirical equations you can use to compute the cb value, okay? So if the lb is greater than lr, then the cb fr value, fcr value will be different, okay? But it will be always less than yield, always less than yield. Please remember, okay, the phi value we are going to use in lrfd will be this one, and the factor of safety which we are using in we are going to use in the asd is 1.7 lrf. Okay, now there are three limit states, okay? There are three formulations, okay? Let me write it down, like I will have to go out of this slide mode and I will add a new slide here, okay? So okay. First is the what is the first, what was the first limit state? Tension, flange, yielding was about this one, and it has to multiply by the tx, okay? So this was the first limit state, and the second limit state was the compression, flange yielding. And in this case, we were having this some R moment reduction factor, and you were multiplying it with the FCR, and I think there was a third factor. Yes, this one. So we were using this equations, okay? But we could not find this one, okay? If the flange is compact, FCR was equal to Fy. If flange is non-compact or cylinder, then you have to calculate this FCR using some empirical equations, okay? But it will be always less than this one. Let me check, am I right? No, there is no upper limit provided here, but I have the feeling that it cannot be less than, it cannot go beyond the Fy value, okay? And the third limit state was LTB.
Okay, sir.
Yes?
Yes, LTP.
LTB. So again, the same formulation, this one, but this was a problem, okay? If this value, for example, if the lateral value, like the stiffness, if this bracing is less than or equal to LP, so there will be no LTB problem, okay? If it is somewhere greater than, okay, oh sorry, if LP, no, let me, I will erase it like this. If LB is greater than LP and less than LR, so you will have some FCR value will be different, okay? This is a problem. You need this one in order to use this equation, okay? This is given here, okay? These are the three scenarios. Is it clear? Somewhat clear?
Yes, sir. Somehow.
Somehow. Okay.
Yes, sir.
Okay, we can take a break and I will have a cup of tea. And when I come back, so we are going to solve an problem, okay, on this. And we will see that how we can use these three limit states and how we can compute the flexure capacity of our plate girder. Okay?
Okay, sure. Oh,
Okay, sure.
thank you.
अच्छा
Yeah.
नींद तो नहीं आ रही आप लोगों को थोड़ी बहुत आ रही होगी uh, let me stop the recording first